Okay, now we're going to look at the rigid bodies. Okay, and so here's our little the coefficient of lift we're going to be doing for our boomerang, um, and we're going to learn about what I is, the moment of inertia, and we're going to compute. You're going to have to compute this coefficient of lift based on the radius that you throw the thing. You're going to have to take measurements of I, and you're going to find R, and you're going to find the coefficient of lift. Those are some of the computations you're going to be doing. Looks scary. I'll walk you through them. You will be fine. Trust me. All right. Anyway, so when we throw something, like um, a rigid body, in other words, must be a solid. Raise your hand if you can think of an exception. Well, that's silly. All right, so here you go. Center of mass of wrench. In other words, if you throw a wrench like this, all right, notice the center of mass where it's rotating around stays right here all the time. And so it's kind of easy to throw a wrench, as you will see here.
If you can dodge a wrench, you can dodge a ball. What? Any other questions?
Sorry, I couldn't help myself. If you can dodge a wrench, you can dodge a ball. But anyway, so if you didn't catch that, it's here for you to watch. All right. I need to put this one in front of you. I'm sorry, I was looking at this. Oh, by the way, on that, I wanted to talk about this real quick. This is the way. This is from physics, a physics magazine, Physics Today, and it's what is cool. The whole reason I put this up here is when he's in his free fall, and the great thing about it was they had all those GoPro cameras hooked up to him. So the great thing about that was when Barnard's God was near the sound of Mach 1, right here, some of the airflow over his body was subsonic, was less. Some of the airflow was less than Mach 1, okay? And shock waves form where the two regimes meet, the blue curve. So right where his speed is going greater than m1, speed less than m1, that sends a shock wave. And that's, he was feeling that. He created a sonic boom, all right? And since his mass was so small, you couldn't hear it, but he felt it. The wave is detached from is a typical for a blunt body moving faster than sound. Baumgartner used his diving skills to maintain a head-down, low-drag position during transonic flight. Transonic means supersonic flight. The drag coefficients for subsonic red data flight are dramatically different. Okay, in other words, when he is going fast, when he is notice the drag coefficient's up around double. A lot more drag than when he slows down. So it's really starting to slow him down. And if you watch that, you saw his airspeed went from like 750 down to about 125. And then they turned it off for his parachute jump. I wanted to show it how it got down to 4 or 5 miles an hour right before he landed. Interesting stuff. Great stuff. Anyway, so we're looking at the center of mass. Rotational dynamics. All right, you're going to be throwing a boomerang, and it rotates. All right, and here's moments of inertia. Here's how you calculate moments of inertia. All right, and none of your calculations are here because we're using a stick. All right, and we've got but anyway, a particle, and all the moment of inertia is, remember how we have mass, which is something's resistance to being moved, and so you got to apply a force to get an accelerator. Same thing here. This is an object's resistance to being spun. All right, so if you put the axis right through the middle of this pipe, 1/12 ml squared is the moment of inertia, where m is the mass of the thing and L squared is the length of it. All right, but if you put it at the end, notice it's 4 times harder to get it to spin. All right. So with and we could almost use as the moment of inertia for our boomerangs. We could almost use this one, but we don't. We use a different moment of inertia. Okay. Conservation means its direction cannot change in the absence of an external torque. This gives spinning objects remarkable stability. So this is why your boomerang spins and it stays stable when it's spinning. I keep picking up the boomerang like you can see me. You can't. All right. And so now we get to the actual boomerangs. So what I'd like for you to do is go ahead, fun and food, right? Returns to it's used for fun and also for hunting. Most boomerangs weren't used for returning back to the owner. They were used for conking some, game on the head so you could eat. Boomerangs are ancient, around 23,000 years old. Here's one that's made out of mammoth tusks. American Indians used them. King Tut's boomerang. Um, so returning boomerangs. Side view, it starts spinning. Boomerang's pushing the air. Air pushes on the boomerang. All right. So if we're throwing it into the computer here, this air that's pushing on the boomerang, it's going to cause it to curve. The spinning is just like a propeller or fan blade, so it would push the air. And then spinning, boomerang pushing the air. By Newton's third law, every action is equal and opposite reaction. So the air also must push on the boomerang. This is what causes it to go. If we looked at it from the top, this is what causes it to go in a circle. Okay? The air makes the boomerang go in a circle just as a rope will make a stone go in a circle. And then here's our simple boomerang that we're going to make. And it's very, very stable. All right, so that's the end of the slideshow. And so go ahead and watch how a boomerang flies. And we will look at this juncture. We will look at the, now we'll look at your pre-lab. I think we're almost there. Always takes me a minute to figure